Okay, welcome everyone, and thanks for tuning in to today's Quantum Gravity and Information Seminar. Today we're very happy to have Nick Hunter-Jones from Perimeter Institute, who is going to tell us about models of quantum complexity growth. Nick, please take it away.
All right, thank you very much. And first I'd like to thank the organizers for this virtual seminar series, especially Hugo, Ignacio, and Ro for inviting me to speak. And I hope that everyone listening is doing well despite the circumstances. So this talk will be based on two papers. Oh, and I should say, feel free to ask questions and interrupt me throughout the talk. I can't see you, but I think if you just either type a question into the chat or unmute yourself, please do so if you need something clarified or have a quick question or something. Good. So this talk will be based on two papers, the first of which came out at the end of last year, and this was joint work with Fernando Brandao, Wissam Chemasani, Richard Kung, and John Preskel. And in this paper, we studied and proved a few things about complexity growth in some different models. And many of the ideas and techniques in this work were due to Richard Kung, who's pictured here. And in proving some of our main claims, we also relied on a result about kind of the randomness generated by random quantum circuits and their design growth. And that's based on a paper which I put out at the middle of last year. Okay, so let's get started. We're interested in quantum complexity, which is a pretty fundamental idea in quantum information. And it allows us to distinguish computational tasks which are easy versus hard for a quantum computer. So say you have some quantum algorithm, which we might want to run on our quantum computer. One might be interested in the circuit depth required to implement it and how that scales, or whether that scales polynomially or exponentially in the number of qubits or the parameters of your problem. So we're very used to thinking about the complexity of quantum circuits, but there's been a lot more recent interest in the complexity of quantum states, especially in quantum many-body physics, where the notion, or where quantum complexity of ground state wave functions has been used to distinguish topological phases of matter. And much more recently, and probably of more interest to the people listening to this talk, it's been conjectured that the complexity of a specific CFT state captures the physics behind the horizon of an ADS black hole. But much more generally, if you're interested in universal aspects of strongly interacting many-body systems, complexity growth is kind of just one underlying phenomenon, along with things like thermalization, quantum chaos, scrambling, entanglement growth. So complexity growth is just kind of one universal feature of the real-time dynamics of these systems. And the complexity of a state or unitary is a pretty intuitive notion. And the traditional definition involves constructing a circuit or fixing some gate set of simple local gates. Yeah, sorry, is there a question? Okay, sorry, I thought there was a question. The traditional definition involves specifying some gate set of two local gates, and then constructing the circuit which implements that state or unitary to within some tolerance. And the complexity is then the minimal size of the circuit that achieves this. So by definition, it depends on the gates that you choose and the tolerance, but I'll give a more precise definition of complexity in a second. And just to specify some notation, we'll be considering systems, well, finite dimensional systems, where the Hilbert space dimension I'll denote with D. And I'm going to be considering systems of n qubits, and I'm going to denote the local dimension as Q. It'll be a convenient parameter to play around with later, such that the total Hilbert space dimension is Q to the n. So n here is the number of degrees of freedom. Okay. So if you've been following the seminar series, you've maybe already heard a lot about complexity growth. And yeah, I guess maybe most of the talks you might have heard about complexity focused on holographic complexity, where the complexity of the time-evolved thermofield double state in the CFT is conjectured to be dual to the volume of an ADS Schwarzschild black hole, specifically the volume on a maximal slice in the bulk. And the complexity of the state has also been conjectured to be dual to the bulk action on something called the Wheeler-DeWitt patch. So there's been a lot of progress in studying complexity growth in holographic systems, as well as extending definitions to understand notion of complexity in quantum field theories. So systems with not necessarily a finite dimensional Hilbert space. And much more recently, this relationship between gravity and complexity has kind of gone in the other direction, where kind of the implications of this conjectured duality between wormholes and complexity, there have been a few papers exploring the implications for theoretical computer science and complexity theory. The statement that complexity grows is much more general and is much more generic phenomenon in many-body systems. So it's believed that the complexity of a simple initial state, so maybe we fix some simple, not so entangled state, it's believed that the complexity grows linearly when we evolve that state with some chaotic Hamiltonian. So some strongly interacting many-body Hamiltonian. And it's believed that this complexity growth continues for an exponentially long time and saturates at an exponential time. So something like e to the n, where n is the number of degrees of freedom. But this also extends to the time evolution operator itself. So e to the IHT is some unitary. And it's believed that the complexity of this unitary for, again, a chaotic Hamiltonian grows linearly in time for an exponentially long time, saturating at a time scale which should be like e to the n. Okay. So this sounds maybe reasonable, but computing the complexity of a specific Hamiltonian and a specific unitary defined by that Hamiltonian analytically is very hard, especially for a fixed Hamiltonian. And this is because you basically need to prove that there are no shortcuts. So naively, it seems like it amounts to enumerating all possible circuits, which might approximate that unitary, and then finding the minimal one. So basically, to come up with lower bounds on complexity, you need to prove that there are no shortcuts. Okay. But we still can give some rough ideas and give some intuition for why we believe that complexity should grow and saturate. So we should expect this kind of early time growth because at sub-exponential times, we should expect that collisions are rare. Right? So the complexity should scale with the time that we evolve for, but but at sub-exponential times, we should think that the likelihood that we'll find some circuit which prepares our unitary with much shorter depth should be pretty rare. And moreover, we can kind of upper bound this linear regime with basically Hamiltonian simulation algorithms. So trotterize your unitary and then kind of break it down into two local gates. These kind of techniques give you an upper bound on the complexity, right? Because that just is a circuit which implements your unitary. So kind of these kind of techniques tell you that at least the upper bound on this growth should be polynomial in T. And an argument for why that the complexity should saturate at late times, we can get by simply counting the number of unitaries in the unitary group. So more precisely, we can just count the number of balls of size delta in the unitary group, and we find that it's doubly exponential in number of degrees of freedom. So something like 1 over delta to the 2 to the 2n. So in this sense, there are this doubly exponential number of unique unitaries in the unitary group. So if we start thinking about the number of circuits we generate as we evolve in number of circuits of depth t, we realize that once the depth of the circuit is something like 2 to the 2n, the number of circuits and the number of unitaries in the unitary group are roughly on the same order. So in this sense, we can really reach any unitary with a depth 2 to the 2n circuit. Okay. So this is some rough argument for why the complexity should saturate at an exponential time, because there are only so many unitaries in the unitary group. Okay. So are there any questions about complexity growth or kind of why we expect these features? All right. So as I said, our goal should be, the goal in this talk at least, is going to be to prove something about this, this early time growth regime. And there are a few ways one might expect to make progress. So one thing you can do is make various complexity theoretic assumptions to prove statements about the complexity of a particular Hamiltonian evolution at very late times. So in particular, these papers by Aronson and Susskind, work by Aronson and Susskind, as well as Bogdanovich and Brandau, they made some complexity theory assumptions, like some complexity classes necessarily must separate. And under these assumptions, they showed that e to the IHT for a particular Hamiltonian has to be super polynomial at exponentially long times. So this is kind of one approach you could expect to take. But the approach I'm going to take to prove things about complexity growth in this talk is to focus on ensembles of time evolutions. Okay.
Sorry, one short point. Or are these expectations universal for any dimension?
Sorry. So here, what do you mean? Do you mean dimension of a dimension of the lattice that I might put my Hamiltonian on, or do you mean dimension of the Hilbert space?
Or like a physical dimension or spatial dimension that you consider?
Right. Yeah. Yes, basically. So I would say to kind of make your question a little bit more precise in the context of this slide, I'd say that if you have some Hamiltonian and maybe you define it on a d-dimensional lattice, I would say that there might be subtle aspects that change, but I think for a generic chaotic Hamiltonian, I would expect these things to be true.
Thanks.
Nick,
yeah.
How is it important, the property of having a chaotic Hamiltonian?
Right. So basically, so again, these are all just kind of maybe like this is all folklore and conjecture. So that's why the purpose of this talk is to try and prove these things for specific systems. But the reason we expect this for chaotic Hamiltonians is because you could imagine if I have some very integrable Hamiltonian, which has a huge amount of symmetry and a lot of structure, I might be able to exploit that to prepare that Hamiltonian and with like a very low depth, with a very short circuit or something. So yeah, I guess these are really features we might expect of generic Hamiltonians. So if you take a bunch of quantum mechanical degrees of freedom and make them interact strongly, maybe this is some behavior we'd expect, along with other things like scrambling and operator growth. So this is kind of one of these universal features that you might expect, but it's hard to prove these things about specific systems.
Okay, thanks.
Yep. Right, so I'm going to be focusing on the ensemble of time evolutions. I'm going to be focusing on our random quantum circuits. And so here's a picture of a random quantum circuit. So I'm going to be considering a 1D system of qubits. So that's this 1D line of n qubits. And a qubit is just a qubit with like a arbitrary local dimension. And I'm going to denote the local dimension to be q. So for qubits, q equals 2. And the time evolution on this 1D chain is going to be defined by the evolution with staggered layers of 2 site unitaries. So acting on all the even links at even time steps and odd links at odd time steps. And where each of these gates is drawn randomly from some gate set G. Okay. And the evolution to time t is going to be given by the product of t layers. So, right, which is the depth t circuit. And the goal is going to be to try and derive exact results for the growth of complexity in this model. So if you've kind of been following some of the more many-body chaos papers that appear on the archive, these kind of models have been really nice playgrounds for things like out-of-time ordered correlation functions and other aspects of scrambling, because they're kind of just nice solvable models that you can work with. And a lot is known about them. So here I've written, so here every gate in space and time is drawn randomly from my gate set G. But I've kind of drawn the circuit with a very fixed geometry, and that's actually not too important. So I can also consider these local random circuits where I just, every time step, I choose a random nearest neighbor 2-site unitary to act with. And the only difference here is kind of just, in the previous circuit, we act with order n unitaries per time step, whereas here we act with just a single unitary per time step. So the scaling of time will pick up an additional factor of n. But most of the results I'm going to say about growth of complexity, at least for this part of the talk, the particular geometry of the circuit is not going to be too important. Okay. So again, the goal is to try and derive exact results for the growth of complexity in this model. And naively, this seems like it's a little, might be pretty straightforward, right? Like if you just hand me this circuit here, it seems like the complexity of the circuit should just be, the size of the circuit. But again, the problem, or the reason kind of lower bounding complexity is so hard is because you need to prove that there's no shorter circuit, right? So you've given me this circuit, it's built out of gates from some gate set G, but to show that, it's the complexity, kind of the optimal way to implement this unitary is actually this circuit. You need to prove to me that there's no shorter way I could have done this. And that's why this is so hard. Okay. Specifically, it's been conjectured by Brown and Susskind that most local random circuits of depth T have a complexity that scales linearly in T for an exponentially long time. So again, this sounds totally reasonable because it just says that, for times that are shorter and circuit depths that are shorter than something like e to the n, there are no shortcuts to implementing this circuit. But again, it's hard to prove because you need to show that, these collisions between circuits of sub-exponential size are rare. And one other thing to note, I find it a little bit more convenient to talk about the depth of the circuit as opposed to the size. But again, this distinction won't be too important. Okay, so are there any questions up to this point?
So can you hear me?
Yeah, I can.
Hi, it's Michael Heller from Potsdam. So I'm a bit confused by the following issue. Maybe you can explain that once again. So you want to consider circuits in which gates are drawn from some random ensemble, but when one talks about complexity, on the other hand, like when one likes to impose the boundary condition that you reproduce a given unitary, right?
Right. So yeah.
Can you explain how to think about it properly?
Right. So really what I'm going to be doing is like, it's a little, at least from my point of view, it's going to be very ambitious to pick a particular unitary and compute the complexity of that specific unitary. So that seems very hard. But what I'm going to want to do is focus on ensembles of unitary. So I have an ensemble at some fixed time t. So in this case, this is like the set of all possible random circuits of depth t, kind of built in this way. And then basically want to try and, instead of saying, here's a particular element of that ensemble, it has to have this complexity. The kind of results I want to derive are things like with high probability from this ensemble, it has to have this complexity, or most elements, most, in this case, random circuits of depth t have to have this complexity. So yeah, in this sense, I'm going to kind of be focusing on ensemble averages, and that's going to make everything a lot more tractable.
Okay, thanks. Yeah.
Does that help?
Yeah, thanks.
Good. Yeah, so the ensemble we're thinking about, it's just some one parameter family of ensembles in time. So, at some fixed time t, we want to understand how many of those random circuits have have some complexity, and we're going to be able to actually count the number of circuits, in that set of a given complexity. Okay. Good. So first, I'm going to just define what I mean by the complexity of a unitary. And then I'm going to derive some results about the complexity of very nice ensembles called unitary designs. And we'll define what that is, but it's a really nice tool in quantum information theory. And then kind of using these results about complexity in designs, we're going to be able to prove statements about complexity for these local random quantum circuits, as well as in a few other models. And then to really make progress on proving this conjecture that most local random circuits of depth t have a complexity which scales linearly in t for this very long time, we're going to use some results about how rapidly these local random circuits generate randomness. Okay. So again, we're considering a system of n qubits with local dimension q. So the total Hilbert space dimension is q to the n. And as I said before, the complexity of a unitary is the minimal size of a circuit built from some universal gate set of two local gates, which approximates that unitary. So I'm going to denote the set of all size R circuits to be G sub R. Okay. And then more precisely, we're going to say that some unitary has delta complexity of at most R if there exists a size R circuit V such that the operators, the unitaries u and v are close. And kind of the distance the measure of distance between u and v is actually going to be in terms of their channels and kind of the distance between their channels, but this isn't that important. But right, so the unitary and the size R circuit are close, and we're going to denote this as that the complexity, the delta complexity of that unitary is less than R. Okay. And so this is the standard definition of complexity in terms of kind of the minimal size of a circuit. We can actually consider a stronger definition of complexity in terms of an optimal distinguishing measurement. And I'm actually not going to talk about this much more beyond this slide, but I'll say that at least in our paper, most of our results were proved under the strong definition. And I think most of the work in that paper was actually was to prove kind of all these results holding under the strong definition of complexity, which Richard came up with. But roughly speaking, we say that the strong complexity of a unitary is the minimal circuit required to implement some measurement, which is capable of distinguishing that unitary from kind of, or the channel corresponding to that unitary from something called the completely depolarizing channel. So a channel is something that takes states to states, and the depolarizing channel is just something that takes every state to the maximally mixed state. So in that sense, you can think about D as roughly the channel equivalent of the infinite temperature state. And the task here is to distinguish the unitary you're given from this kind of maximally useless channel with restricted measurements. So if your unitary is very simple, you might imagine that you can perform a simple measurement to distinguish these two. But if it's very complicated and very entangled, you'll probably have to perform a very high depth, or like a very complicated measurement in order to distinguish the two. And we can also prove that this definition is stronger than the previous one in terms of the minimal circuit depth, but everything I'm going to say holds under both definitions. Okay. So as I said before, we're kind of interested in understanding the average complexity of random quantum circuits of a given depth. But to make progress, I'm going to use, we're going to derive some very general results about the complexity of very nice ensembles called unitary designs. But first I need to tell you what a unitary design is. So I'm first going to kind of give a more formal definition and then try and explain it in a more intuitive way. But remember that the Haar measure is the unique measure on the unitary group, UD. And we can define the average of an operator kind of over this ensemble in terms of something called the k-fold channel. So if we consider some operator acting on k copies of our system, you can think about the average of the operator is roughly this, defined by this object called the k-fold channel. So instead, if we're interested in some ensemble of unitaries, so this is some weighted subset of the full unitary group, the k-fold channel of an operator averaged over that ensemble is then just given by this expression. And we say that an ensemble of unitaries is an exact k-design if these two objects are equal for all operators. Okay? So for every operator acting on your k-fold system, these two things are exactly equal. So basically this is asking when the average over some ensemble, so some subset of the unitary group, looks like the average over the full unitary group. Right? So you just have this big unitary group and maybe you have a set of points on that space and you're just asking when averaging over that set of points looks like the average over the full group. Okay. So for k equals 1, we know that Pauli operators form an exact one design, but in general, very little is known. So very few exact constructions are known. So we can kind of relax these definitions and ask when an ensemble is close to forming a design. And we say that an ensemble is close to forming a design. Basically, it forms an epsilon approximate k design if these channels are close in this norm called the diamond norm. And designs are a very powerful notion in quantum information because they kind of allow you to wield the the power of the full unitary group with relatively low complexity. So here's a more intuitive way of explaining what a design is. So if an ensemble of unitaries, so some subset of the unitary group, forms an exact k-design, this is the statement that the average of the average over that ensemble is equal to the average over the full group up to the kth moment. Okay. And if the ensemble of unitaries forms an approximate k-design, then the average over that ensemble is close to the average over the full unitary group up to the kth moment. And it's close to in a way that you can control. So I'll maybe give one more slide about intuition for designs. So you might imagine thinking about how random the time evolution of a system is compared to the full unitary group. Okay? So you could consider some ensemble of time evolutions like we were doing before at a fixed time t. So these could be random circuits like we talked about before, or they could be disordered Hamiltonian. So some ensemble of unitary time evolutions at a fixed time generated by some ensemble of disordered spin systems, or for SYK model, for instance. And at time equals 0, right, you just have a bunch of points sitting at the identity. But time evolution is going to move us in this for chaotic systems is going to move us rapidly and ergodically over the unitary group. So you could imagine quantifying how random that time evolution is by asking about when that ensemble forms a design and starts approximating moments of the full group. So is the notion of a design, of a unitary design, somewhat clear? Are there any questions about this?
Sorry, I just wanted to ask, can you prove that exact k-designs always exist? Or
Yeah, actually you can. So I don't, yeah, well, there are, I think basically you can prove that discrete designs exist for any space, but in particular for the unitary group, you can prove that exact designs exist for any dimension and any k, and that they and you can also prove that minimal designs exist. So basically, you know, lower bounds on the kind of cardinality of these sets have to be saturated.
thank you.
Yeah, but so we know they exist, but we really just don't know much about them in this exact case. So we kind of, for k equals 1, 2, and 3, we know examples of exact designs, but for general k, very little is known. So that's why we know a lot more about approximate designs. So ensembles which get close to capturing these moments. Yeah. Any other questions? Okay. So so I'm now going to consider a discrete approximate unitary design. So this is again some nice set of unitaries. And we might imagine asking if kind of the structure of a design allows us to prove anything about the complexity of the elements of that design. And the answer is yes. The structure of a design is sufficiently restricted that we can basically count the number of unitaries of a specific complexity. So more precisely, we can kind of prove the following two statements: that with very high probability, so exponentially close to 1, a unitary U drawn from an approximate design has complexity which scales roughly linear in n and k. So I've kind of dropped I've just simplified this and dropped the dependence on delta and dropped some constants. But roughly speaking, with high probability, the complexity is going to scale linear in n and k. And moreover, you can kind of do a little bit better than this. You can actually directly count the number of unitaries of a given complexity. So you can kind of use a bound on these weights to restrict the number of potential collisions and kind of directly count the number of unitaries of a given complexity. And you find that like there are exponential, so e to the nk, an exponential number of distinct unitaries with this maximal complexity, or with this complexity here. And the more formal statement is that an epsilon approximate unitary k design, so this ensemble of unitaries, contains at least this many distinct unitaries with complexity greater than r. Okay, but roughly speaking, for complexity linear in n and k, this is exponential in nk. Okay. So now back to random circuits. You should think about this result as roughly saying that the average complexity of this ensemble is scaling linearly in k. So if we go back to random circuits, we can use this these local random circuits, we can use this very powerful result from Brandau, Harrow, and Hordetsky, which says that for basically moments up to square root in the total dimension, the set of all local random circuits of depth t forms an approximate design if the circuit depth is on the order of k to the 11 times n, okay? Where c is some potentially large constant, which depends on the gate set we choose. But roughly speaking, this is saying that random circuits of depth n times k to the 11 form designs. Okay. And we can now combine these two results to say something about the complexity of local random circuits. So again, obviously at very early times, we expect that the complexity should be roughly equal to the size of the circuit. But to prove this, we must account for collisions. And we know that these collisions must dominate at exponential times as the complexity saturates, right? And so, you know, lots of different random circuits are becoming approximately equal. But the structure of an approximate design allows us to restrict the number of potential collisions and count the number of distinct unitaries of a given complexity. So combining the previous two results, we find that with very high probability, a random circuit of depth t has complexity which scales like t to the 1 over 11. And moreover, the set of depth t random circuits contains an exponential number in t to this funny power, distinct unitaries with this complexity. So I'll recap in a second, but this establishes a polynomial relationship between the growth of complexity and the depth of the circuit up to very, very late times. But as we saw in the thing we actually set out to do was to prove a linear growth. Okay, so this complexity by design result, basically we said that the average complexity of the ensemble scales linearly in k. Okay, for a unitary k design. So and then we use the result that local random circuits form designs to get complexity scaling kind of to give this slow complexity growth, right? So we were able to relate the complexity of designs to the design order k. And so if you just hand me some ensemble of time evolutions, which is forming designs, that'll give you some growth of complexity. But in this case, it kind of gave us this relatively slow growth to this, you know, t to this 1 over 11. Okay. But as I said, anytime you have some ensemble of time evolutions, which is forming designs, we can use this design growth result to prove statements about their complexity growth. I should actually stop. Like, are there any questions up until this point about what we've done? Okay. Right, so we can kind of plug in different design growth results for various models and prove statements about their complexity growth. So for instance, in these Brownian quantum circuits, so these are kind of all-to-all coupled spin systems with disordered and time-dependent couplings. So it's known that the design time is similar to the random circuit case, scales like k to the 11. And this again gives a very slow complexity growth, this t to this weird power. There's a model of basically nearly time-independent Hamiltonian dynamics. So some time-dependent Hamiltonian where the couplings change slowly in time. And it's also known that these Hamiltonians form k designs in n squared k time, so linearly in k, but only up to a very short time. So this is roughly saying that translating this into complexity, this gives a very short time complexity growth up to a time scale that's like square root n. But it is actually linear in t. Okay. And it's also known that higher dimensional random circuits, so defined on higher dimensional lattices instead of this 1D chain that we've been talking about, also form designs with this better scaling in n, but to some very high power in k. So this again gives you some very slow and sublinear complexity growth. Okay. But at the very least, we can prove, you know, these statements about complexity growth in these models. But what we really set out to do was prove a linear growth of complexity for random circuits. So in order to show this, what we need to, we had this linear relation between complexity and the design order K. And what we would need to show that complexity is growing linearly in time is to show that these random circuits form designs linearly in K. Okay? And moreover, a lower bound on the K design depth is known. So a lower bound on the depth for random circuits is known to be linear in N and K. So basically the thing you need to prove is that random circuits saturate this lower bound and are thus kind of optimal implementations of randomness. So they form designs kind of as rapidly as possible. Okay? So to get this linear growth in complexity, we really need this linear growth in design. And this kind of brings us to the last part of the talk. So are there any questions up until this point? Okay.
So this t to the 111 is supposed to be, well, I mean, it's some bound on the rate.
That's right.
What you're saying is that it's possible that the rate is higher.
Yeah, right. So this, yeah, this is some nice theorem. This is saying that, like, at the very least, you need a design depth which scales like this, but you could imagine doing a lot better. So for example, it's known that like kind of optimal is just K, like this is the optimal scaling in N, but you can do a lot better in K. So yeah, basically it's saying there's a lower bound on what this optimal rate is, and it's known to be linear in N and K. And in fact, like kind of saturating that lower bound is what we need to show that complexity grows linearly.
And from the point of view of these various physical systems that you discussed on the previous transparency, I mean, do they, well, I mean, like, would you consider them as exotic systems, or like you expect them as, or you see them as something that, is quite natural from the point of view of what kind of systems we're interested, say, in holography?
Yeah, so from a holographic point of view, they're maybe not natural. I guess natural kind of depends on what your taste is. I think from the point of view of maybe people doing holography adjacent things like this many body scrambling stuff, these are very natural systems. And the reason they're natural is just because you can prove a lot about them. Well, like they kind of, it's easy to see, or the reason people like them is it's easy to see that like OTOCs decay and that like entanglement grows in this way, and you can compute things like operator growth. So they're nice systems to work with. And from an experimental point of view, they're also pretty reasonable. So for example, these types of random circuits are also the ones that come up in these quantum supremacy experiments. So to show that, so in the recent Google experiments, kind of the architectures they chose were more like these higher dimensional random circuits.
So one more question related to it. So
yeah,
I guess like when you started, like you did not care that much about locality in real space, right? I mean,
no, actually,
are your gates like really local? Like, I mean, like they couple the neighboring two legs, or they can couple any two legs?
Yeah, no. So yeah, I tried to make that clear at the beginning, but maybe like yeah, all the models I'm considering, and I think all the models listed here are all for local interactions. So all of the gates kind of act on a neighboring pair of qubits. So they're all nearest neighbor to local gates.
Also this Brownian quantum circuit?
No, actually, sorry. Yeah, actually, that's a non-local spin system. So that is all.
Okay.
Yeah.
Okay.
But the ones I were considering were kind of these, the geometries like kind of might be random, but like the interactions are always local.
Okay. And do you expect a spatial locality versus spatial non-locality but still like 2 to 2 gates? Does it matter for?
Yeah, that's a good point. So probably for all these statements about complexity growth, not much is going to change. The thing you actually expect is that like so here kind of like so I'll yeah, if you want to ask questions about scrambling, for instance. Both of these circuits scramble in a depth in a time that's like order n. But if you were to start acting with these long range gates, which maybe say act on 2 qubits kind of non-locally, so there's all-to-all interacting in that sense, then the scrambling time should be log n.
Mm.
But I think from a QI standpoint, I don't think that's rigorously been proved. But I think if you consider these non-local circuits, like you said, all of the n, linear and n scalings I've written should all change to log n's.
Oh, I see, I see.
Yeah. But the reason I'm actually not considering those is because that's very hard to rigorously prove. So
I see.
it's just a lot easier to prove things about these local random circuits, and a lot less, I guess, is rigorously known about these all-to-all interacting circuits. But,
okay, thanks.
yeah, but yeah, you're right. Generally, more randomness means everything gets faster. So you would expect that, like with these all-to-all circuits, the scaling in n should improve. But I think this scaling in k should be the same. So the complexity growth should also roughly be the same. And maybe one, just because you asked about a comparison to holography, and there are probably a lot of holographers listening. So yeah, I guess these systems are nice because they kind of do the things you expect in holography, like all the chaosy things you expect in holography. But the reason they're a little bit less physical is like all of these systems are time dependent. So and that's for these random circuits, right? My Hamiltonian is changing at every time step. And this randomness in time is actually pretty important for kind of showing that they form designs. And I think, yeah, I think this randomness in time is at least important in kind of in the proofs I'm presenting for computing the complexity growth. Now, like, yeah, I guess there are a few more holographic-like systems that do have this randomness. For instance, you could consider taking SYK and taking the disordered couplings and then making them time dependent. I don't think this has been studied in detail in kind of the context of designs, but I think that should be another system which does form designs quickly. But I think if you actually take some fixed many-body Hamiltonian, which does have energy conservation and does kind of evolve in a time-independent fashion, then probably just a different proof technique is needed. I think this design approach might not be great. But yeah, are there any other questions? Okay, all right. So right, we're studying these random circuits. We want to prove a linear growth of complexity. And to do that, I need to show that they form, they kind of form these nice ensembles. They form unitary designs as fast as possible. So that actually brings us to the last part of the talk. And here, basically, I want to use like some nice tricks to show that random circuits kind of saturate this lower bound and form designs in this kind of optimal depth, at least if you take the local dimension to be large. Okay, so the statement is that random circuits, these local random circuits on n qubits with local dimension q, form approximate designs when the circuit depth is linear in n and k, once you take the local dimension to be large. Okay, so again, this is the system we're studying. We're studying these evolution of these staggered layers of unitaries acting on a 1D chain of qubits, of n qubits with local dimension q. And we're studying the convergence of this the set of random circuits to unitary designs. And actually, for this part of the talk, I'm going to pick this local gate set to be actually just the unitary group on the two sites, the Haar measure on the unitary group on the two-site Hilbert space. Good. So I'm going to focus on something like kind of the two-norm distance to randomness and analytically compute a quantity, which I'll describe on the next slide, called the frame potential. And kind of making use of some nice ideas in these papers, it turns out you can write this object as a lattice partition function. And we're going to be able to compute this lattice partition function exactly for low moments. But for very general moments, we're going to need to kind of just sacrifice some precision and come up with upper bounds. But we'll see that this decay to hard randomness has some nice interpretations in terms of domain walls in this lattice model. Okay, so we defined approximate designs before. So we're just interested in when some ensemble of unitaries looks like the Haar measure. So a nice object to consider is this kind of double average over the ensemble. So it's kind of the sum of all the inner products between pairs of unitaries in your ensemble to some power. And you can show that for any ensemble of unitaries, this quantity, the frame potential, is lower bounded by its Haar value, which turns out to be k factorial. With equality if and only if you form a design, right? So if you just give me some ensemble of unitaries, this is just for a given k, this is just some number you can compute, and how close that number is to k factorial tells you how close you are to forming a design. And it's related to the more precise definition I gave of an approximate design before, just up to some dimension factors. Okay. So this is some number we can compute, and the ensemble we want to consider now is the ensemble of random circuits of depth t. So we want to compute this double average over the set of random circuits. In doing so, we're basically doing a kth moment calculation of these random circuits. We have k copies of the circuit and its conjugate. And we're basically going to average over each of these local gate sets. And when you do so, it turns out you can write the entire frame potential is just the partition function on a lattice model. You can exactly write this, this entire object here as a lattice partition function. And the result is that the kth frame potential is basically the sum over all possible spin configurations of this triangular lattice, which has width n over 2 and depth 2t, and with periodic boundary conditions in time. So all these spins here are identified with these ones on the left. And the local degrees of freedom in this partition function are elements of the symmetric group Sk. And these plaquette terms, so these functions of 3 spins, are, again, it's not quite important what they are, but they're just some functions we can compute. Okay. So this quantity, which is this distance to Haar randomness, just has this nice interpretation in terms of this lattice partition function. Okay. And as I said, it's lower bounded by its Haar value, k factorial. So the closer this thing is to k factorial, the closer the ensemble is to forming a design. So what one can do is show that for plugging in the same spin everywhere, so plugging in the same element of Sk everywhere, gives these triangular plaquettes just have weight 1. So the entire thing has weight 1. So there are k factorial configurations which give you weight 1. And in this sense, we see that the minimal Haar value is kind of coming from the k factorial ground states of this lattice model. Okay. So to show that random circuits are becoming random, basically you need to understand how all these higher order terms are decaying, right? And such that this whole thing is becoming close to k factorial. And it turns out that the good way to think about all the excited states, so all the kind of non-trivial spin configurations, are in terms of domain walls, which wrap the circuit. So for k equals 2, so this is like the second frame potential. The local degrees of freedom are just elements of S2. So that's just the identity permutation and the swap permutation. So here's a possible single domain wall configuration in the k equals 2 case. Here's some possible double domain wall configuration. And it basically turns out that for any k, you can think about this, basically all the contributions to this partition function, this frame potential, as complicated domain wall configurations. And all you need to do is to upper bound this quantity. You just need to count these basically all possible domain wall configurations. But this decay to Haar randomness has this nice interpretation in terms of domain walls. So as we time evolve, right, I said all excited states are, can be thought about in these terms of the domain walls. As we time evolve, the random circuit becomes deeper, and thus these domain walls stretch, giving a higher energy contribution to the partition function, and thus, decreasing weight. So that's one way to interpret kind of this decay to Haar randomness. So it turns out basically you can compute the k equals 2 frame potential for random circuits, and I've just written kind of a simple upper bound here. And that allows you to extract the circuit depth at which you form an approximate design. And simply speaking, in this case, it's just linear in n with a log 1 over epsilon for the error term. And this is a result that's known, albeit with an exact calculation and an exact determination of the coefficients. And just in case it's of interest, you can actually compute this partition function, this k equals 2 partition function exactly, by solving a problem of many non-intersecting random walkers in the presence of boundaries. So it's nice, it's something you can compute exactly, but we're really interested in the kth frame potential because we want to understand how quickly we form k designs for all k. And for very general k, the domain wall configurations that are allowed becomes much more complicated. And an exact treatment, the domain wall combinatorics are no longer quite as amenable to an exact treatment. But what you can do is prove an upper bound, which is really all you need on this partition function, in terms of a contribution from the ground states and the kind of a simple set of domain walls. And you can prove that all the higher order terms, which you don't know how to compute, are suppressed if you take the local dimension to be large. So basically you prove that there are kind of, just the ground states and these first excited states. And then, technically to upper bound this quantity, you need to bound all the excited state terms, but which seems like it amounts to at least having some combinatorial handle on how many of them there are. But just by taking the local dimension to be large, you can prove that they're suppressed. So in this limit of large local dimension, you can extract the design time and it for these random circuits, and it turns out to be linear in n and k. Okay. So so what we've done is we've shown that random circuits form unitary k designs in a depth which scales, again, linearly in n and k when we take the local dimension to be large. And again, as I said, a lower bound on the design depth is known to be order nk. So random circuits are thus optimal implementations of designs. So I could only show this, or we could only show this in the large Q limit, but I gave a number of reasons why I think there are a number of reasons why this limit is not probably not necessary. So a lot of the terms there are a lot of terms which basically you can drop, and some of the terms are negative. So if you're trying to upper bound them, you can just drop them. And kind of like in the multi-domain wall terms that you can compute, you can just show that they decay kind of faster than you need, but this doesn't really constitute a rigorous upper bound. So I just left it as a conjecture that this large Q limit isn't necessary, and that the kind of these simple domain walls for this partition function dominate kind of the multi-domain wall terms. And if this were true, then you can show that random circuits form designs even for qubits. So without having to take Q to be large. All right, and so I'll go back to complexity now. So this allows us to basically establish the conjecture that we set out to prove for local random circuits with a large local dimension, right? So we had that we knew that complexity scaled linearly in k, and we just needed to show that the circuit depth to form designs, so this times also scaled linearly in k to prove a linear complexity growth. So the precise statement is that local random circuits of depth t have complexity t, and moreover, you can kind of go in and directly count the number of in this set of random circuits, which and count the number of elements of a given complexity, and show that there are at least an exponential number of distinct elements with complexity t. Right? So for random circuits with large local dimension, we've shown that the complexity is growing linearly in time for a long time, and moreover that the number of unitaries with this maximal complexity, so in this case generated by time evolution to time t, so depth t random circuits, the number of distinct unitaries of this complexity is scaling exponentially in t. Right? So the complexity is growing linearly in t, but the number of elements with this complexity in that set is, so the average complexity is growing linearly in t, but the number of elements with this kind of large complexity is in that set, the number of distinct elements is scaling exponentially.
Nick, a quick question. Do you have, or does your argument have something to say about the saturation?
Right. I'm just trying to decide if I should finish before answering that. Basically, no. So maybe I'll just skip to one of my backup slides. Yeah, so basically what we've done here is just we've just rigorously, at least in this very simple case of random circuits, just kind of proven something about this early time regime. You might also be able to, basically we also understand this, for random circuits, we also understand this very late time regime. But I would say, just because you know that you kind of get arbitrarily close to forming, to capture, like arbitrarily close to fully random unitaries, kind of at these very late times. But these linear growth bounds I presented kind of break down at a time scale, which is like square root of the dimension. So this is like e to the n over 2. So I would say that, like, to answer your question, no, there's like this kind of transition regime here is still pretty mysterious. And in the context I presented, this is kind of this is like a very high moment regime. So this is like when this K in the K design, when the moments you want to consider are like the order of the dimension. So yeah, this is definitely something that still needs to be worked out.
Okay, thanks.
Yeah. Right, so I can end here. So what we've done is we've just proved this long time linear growth, at least for random circuits with large local dimension. But as I said, we kind of, to make progress, we had to consider an ensemble of evolutions. So the most a naive question, or like we might set out to do, or something that we would like to do, is just ask if we can prove anything about the complexity for a fixed Hamiltonian. So can we prove anything about this thing for some fixed age? Yeah, it would also be nice to rigorously kind of bound these higher order terms in the partition function, and show that this large Q limit wasn't necessary. And just as was asked, there are also some confusing things about this late time regime. So kind of this time scale at which the complexity saturates, which happens when the design order is roughly the dimension. I also think that these StatMech methods are very powerful, and probably just studying, yeah, they probably have a lot to say about the pseudo-randomness properties of other random circuits, and they're also probably very useful for computing things like entanglement growth. So I think if you have random circuit, some quantity you're interested in for these random quantum circuits, these StatMech methods are very useful. And lastly, I only briefly at the beginning mentioned this strong definition of complexity, kind of in terms of an optimal measurement. But I think there are a few reasons why this might be more suited for holography. But yeah, I'll end there. So thanks for listening.
I had a question.
Yeah, please.
Yes, so you mentioned about this linear growth of complexity for some time. So when you showed the graph, that had an overall linear trend, but there were some fluctuations.
Oh,
so,
right.
So are these like determined by, so are they like order 1 by n or something, where n is the dimension of the Hilbert space, or like, does one know what determines the size of these fluctuations?
Yeah, the short answer is no. Yeah, so for kind of averaging over the entire ensemble of unitaries, right, this is an exactly linear growth. But what you might ask, so this, that's a statement and expectation, but what you might ask is, if I take a given random circuit, so a given element of this ensemble, how, with what probability does it deviate from the average, right? Mm-hmm. So that's kind of what you mean by these fluctuations, right? So for a given instance of this ensemble, how large are these fluctuations?
Yes.
And I would expect that they are, probably large at early times and become suppressed, but I actually don't know how to prove that. So yeah, that's a good question. Kind of bounding the size of these fluctuations for fixed circuits at late times. It's a good thing to work out.
I see. What are the sort of models? Is there any model in which this thing can be calculated analytically at all? This growth of complexity?
So you mean for a fixed area, or yeah, what are you asking specifically?
No, I'm just asking if there is a specific model in which you can actually analytically compute this complexity.
But for instead of like making ensemble average statements for fixed
Yes,
Hamiltonian,
yes.
yeah, not basically no. So I would say that like computing complexity of like a fixed unitary or a fixed Hamiltonian evolution kind of needs to be an incredibly hard problem. And there are a bunch of complexity theoretic reasons why you expect that to be true. So I guess very generally you expect that, yeah, even if you did have some Hamiltonian and you knew that there was some circuit that approximated it, you would need to go in and rigorously bound, rigorously lower bound the complexity, which amounts to proving that there was no possible shorter circuit. So there are probably, yeah, I would say that there are probably ensembles of Hamiltonians where you might be able to kind of better grapple with that question. But yeah, I think there are no results that I know of kind of in the direction you asked. And in general, it must be a very hard problem, or we know that it must be a very hard problem.
I see. Okay, thank you. Thanks for your talk.
Yeah.
One more question.
Yeah,
so
please.
I'm wondering, can you transfer your results to continuous systems and quantum field theories?
Yeah. Like actually, not so simply. Yeah, even for quantum mechanical systems where you take the dimension of the Hilbert space to be large, there are a few confusing things that pop up. Specifically, I get very confused about designs even in the case of infinite dimensional quantum mechanical systems. So yeah, I mean, I think probably this is true for it's probably true that strongly coupled field theories do have, with a suitable definition of complexity, which I think has been proposed probably by people that are in the virtual audience. So I guess we have some understanding of what complexity should look like for a field theory, and probably for a generic strongly coupled field theory, this linear growth should be true. But kind of all the techniques I showed, I don't know. I don't think they would work. I think kind of this method of using unitary designs really does require a finite dimensional Hilbert space. So probably just the proof techniques would need to change.
Thanks.
Yeah.
Any more questions? Okay, then if not, let's thank Nick again. Oh,
I have a question. So sorry for jumping in last minute.
No,
do you have also something to say about say ground state preparation using these ideas, or this is specifically tied to time evolution?
I mean, definitely, yeah. Complexity has a lot to say about preparing ground states, and yeah, that's a good question. Yeah, off the top of my head, no, but yeah, I don't see how you would kind of, yeah, there's like definitely complexity is very relevant for kind of, how simple it is to prepare ground states, but yeah, I have nothing to say about direct connections from what the work I presented here, but it's definitely a good question.
Okay, thanks. Sorry, Ignacio.
any more questions? Okay, if not, then now let's thank Nick again.
All right, thanks everyone.
Thanks, Nick.